In this video, we're going to start discussing triple integrals. A single integral back in single variable calculus was defined on an interval on the real line, and it was defined by breaking up the interval into a bunch of subintervals, picking a point in each subinterval, forming a rectangle on each subinterval where that particular point that was chosen was used to determine the height of the rectangle, and then summing those rectangles together, eventually taking the limit as the number of rectangles goes to infinity. In one of the previous videos, we did a similar thing with double integrals. A double integral is defined on a region in the plane, and we were able to break up that region into small rectangles. We chose a point in each of those small rectangles, and we built a rectangular column on top of each of those rectangles where the height of the column was determined by the function value at the chosen point in that rectangle. So to extend in the obvious way to a triple integral, what we're going to need is we're going to need a function of three variables, f of x, y, z, and it needs to be defined on a solid, on a closed solid, which we'll call S, which is a subset of R3, so of 3 space. A standard interval from single variable calculus was involved a function with one variable defined on a portion of the real line. A double integral involved a function of two variables defined on a region in the plane. And here we have a function of three variables that's defined on some portion of three-dimensional space. We're going to do the same sort of process that we did for the other types of integrals. We either broke up the interval into subintervals, we broke up the region into rectangular regions. In this case, we're going to break up S into boxes, to rectangular boxes, with volume dV. We're going to choose a point in each of these boxes. All right, so we might call this point x, I, j, k star. We're just going to use this once, so don't worry so much about the notation. But we have a three-dimensional grid of boxes. Those boxes are going to be indexed by I, j, k. And the star just means we're picking a particular point in that box. All right, so each box now has a chosen point. We're going to form a Riemann sum. Which will simply be the function value of this particular point that we just chose, taken at all of the different boxes, and then summed up. And so for the double integral, we had a double sum. We had to go in the x direction and the y direction. And not surprisingly, here we're going to have a triple sum, one in each of the three directions. So this is going to be the k equal 1 to L, j equal 1 to M, and I equal 1 to N of the function value of our chosen point, x, I, j, k star, y, I, j, k star, and z, I, j, k star, and then dx, dy, dz. Right? And then once we have the Riemann sum, we take the limit as L, M, and N, all three go to infinity. Right, so this is going to be a triple limit. We're going to take all three of these quantities to infinity, and that means we're going to look at the more and more boxes in all three of the directions, which means we're going to break up this region into sort of a very, very large number of boxes, compute the volume, of each box and then, or compute the point from each box and evaluate our function at that point. And as the boxes get more numerous in each of the directions, the size of the boxes are getting smaller and smaller, so that eventually these boxes get closer and closer to just being a single point. And once we take the limit, then we can think of each point as its own box, and then that sum in the limit will actually give us the precise value. Right? So our precise definition is just taking the limit of what we just looked at. So if we have f, just like before, if we have a function f of three variables defined on a region S of 3 space, we have the triple integral over S of this function dv. And it's going to be defined as the limit as L goes to infinity of the limit as M goes to infinity of the limit as N goes to infinity. So a triple limit of a triple sum. So k equal 1 to L, j equals 1 to M, I equals 1 to N of our function evaluated at our chosen point dx, dy, dz. All right, so this is going to be our definition of a triple integral. It's very natural, an extension of the single and double integral definitions. And very much like single and double integrals, you do not want to use this definition to compute an integral. As the dimensions get more, these integral definitions get even more unwieldy. And so we have a version of Fubini's theorem that applies to triple integrals. And so we're going to start with functions f of x, y, z, which are continuous on a rectangular box. All right, so we're going to look first at a function defined where S, capital S, is a rectangular box of the form PQ cross RS cross TU. All right, so like with double integrals, this notation means that X ranges from P to Q, Y ranges from R to S, and Z ranges from T to U. So if the function is continuous on this box, then our triple integral that we have defined above is defined by the iterated integral from T to U, from R to S, and from P to Q of our function dx, dy, dz. Right, so this is our iterated integral. Works the same way as our double integral Fubini's theorem version. And in addition to this, any reordering of integration will yield the same result. Right, so in this case, I chose to integrate with respect to x first, then y, then z. Because all the limits are simply constants here, we can simply move around whichever order we want. There's actually 6 orders that we can differentiate these 3 variables in. And so there's 6 different iterated integrals that we could compute, and all of them will yield the exact same value. All right, so let's take a look at an example. So let's say we wanted to evaluate the triple integral of the function 3x squared y minus xyz cubed dv. And my region S in my rectangular box here is going to be the box defined by 1, 3, negative 1, 2, and 0, 2. Right, so we're going to take this rectangle and define this integral, this triple integral, on this rectangular box in 3-dimensional space. Right? So Fubini's theorem says our first step is to pick an order of integration. And also that it doesn't matter what order we pick. So unless there's a particular reason we might pick a certain way, a lot of times it does not matter how we do this. So this one, if we do in kind of the same way as Fubini's theorem, we'll do dx, dy, then dz. So this will be the integral from 0 to 2, the integral negative 1 to 2, the integral 1 to 3 of this function. So this will be dx, dy, dz. All right, and now we just compute iterated integrals as we did with double integrals. So we'll compute the inside integral first. So first integral, we're differentiating with respect to x. So when we anti-differentiate this function, we're going to get 3 times x cubed over 3, so the 3's will cancel. And so we have x cubed y minus 1/2 x squared yz cubed. And that's going to go from 1 to 3. All right, so when we substitute in the limits of integration here, we're going to get 27y minus 9/2 yz cubed minus y minus 1/2 yz cubed. All right, we put that together. And we have 26y minus 4yz cubed. So now we've evaluated the inside of the 3 integrals, and now we just have to repeat this process and compute the other 2. All right, so the next step is to compute the second iterated integral. And so we want to anti-differentiate 26y minus 4yz cubed. And when we do that, we're going to get 13y squared minus 2y squared z cubed. And that's going to be evaluated from negative 1 to 2. All right, remember, in that integral, we were differentiating with respect to y. Right, and so we evaluated our endpoints here, and we get 13 times 4, which is 52, minus 8z cubed. And we're going to subtract from that 13 times 1, which is 13, minus 2z cubed. All right, and so we combine all that together, and we get 39 minus 6z cubed. And now this is just a single integral of a polynomial. And so the antiderivative is 39z minus 3 halves z to the fourth. And we're ranging from 0 to 2. And so we have 78 minus 3 halves times 16, which is 24. Right, when we evaluated 0, both terms are 0. And so 78 minus 24 is 54. Right, and so the value of this triple integral over this rectangular region is 54. If you'd like to practice a triple integral like this, you could actually compute the same one. Just switch up the limit of integration. I differentiated with respect to x, then y, then z. So there are 5 other possibilities for you to try. And in each case, you should get 54. And so if you get 54, most likely you did this correctly. It's going to be difficult to do, kind of get a fluky answer to this. But you should get 54 in all of those other 5 cases.